problem. I gave you a problem in that. I don't know why I stopped that. I think I was going to say something else that I'm not going to say now that it's recorded. But I'll say it at the end of class. So let's do a quick overview so that we can talk about this shit together. So you've got a subgroup H in G, and you can form all these cosets, right? So I can form cosets of H. If it turns out that H has all its left cosets equal to its right cosets, what is it called?
It's a
normal subgroup. Then H is normal in G, and we make the subgroup sign, but then we close it off and turn it into a little triangle. So that symbol universally means normality of the subgroup in the group. And again, that just means these are the same. Now this doesn't mean, and I really want to make this clear, this does not mean that AH equals HA for all H and H. What does it mean? It doesn't mean this.
It means all the left cosets are equal to all the right cosets, doesn't it?
Yes, that they're permutations of each other, but it's not necessarily the same element. So what it means is that if you take some H out of here, you've got AH, you form that there's some element over here, H prime, which when multiplied by A gives you the same result. So these are basically, these are kind of permuted versions of each other in general. Left and right cosets. And I think we've seen this not be true. We've definitely had examples where the left cosets and right cosets are not the same. There are many places where this is automatically going to be true. For example, if G is abelian, then this actually does hold true for all the elements. So if I have an abelian group, every subgroup is normal inside of it. And then there's some other properties that I may or may not have talked about. I can barely remember what happened on Monday, but yeah, I'd say Camille is still, yeah. So once I have a normal subgroup, I can form what's called the factor group. So assume H is normal in G, and we create this new group structure, and you can read this as G mod H. And this has a really cool effect on things. So what it says is form all the cosets of H and notice how things coalesce. And we've seen that different cosets, you can have different representatives, but they end up being the same coset. So what it's going to do is it's going to take your group G and it's going to pool it into these disjoint cosets. And you just grab any representative you want out of there. And we're going to treat these sets as individual items. So the whole set now becomes an object unto itself. This G mod H equals all, you could make this all left or right cosets because it doesn't matter, but we just basically say all left cosets of H in G, and the group operation is that if I have one coset, AH, and I multiply that by another coset, BH, then that is performed by just taking the representatives, doing the group op on them, and then forming that new coset. So you're not like multiplying that by that, by that, by that. You just take these front two, get your new coset that way. And this forms a group structure once we have that. So and for this to be well defined, for this to even work, you need normality to make that happen. So this forms
with that, there's like the assumption then that like what modular arithmetic, like we've got associativity and we also have like inverses.
all that good stuff. So all those group properties also come from this. Yeah, so for example, if I have AH, its inverse would just be that.
Oh, because G is a group.
Yeah. Does that make sense?
Yeah.
So you're right, because these guys follow group laws, then all that stuff is gonna come.
Just to clarify the notation for that is just a vertical line, it's not a slash, right?
That is a slash.
Oh, it is a
actually.
slash.
That's like a division,
Okay.
and it's because of that, it's suggestive of what's happening here.
Sure.
We're dividing out all similarities according to age.
Okay.
Is that,
Yes.
yeah, kind of?
Mm-hmm.
Yeah. So, yeah, we're pooling things as H would pool them. And let's see, if for those who watched it, I gave a couple of really kind of challenging problems at the end. Let's talk about those problems. And I'm curious, did you get anywhere?
So you're talking about like the external direct sum ones? that you
Yes.
sent? Those were really weird.
Those are fucking crazy.
Yeah.
I've spent a lot of time trying to think about how to talk about those in here, but I love them. So
Yeah.
let's actually talk about them just a little bit. So please, if you haven't watched that half-hour recording, do that, please. It's gonna help you. So, oh, and by the way, did you see I put some stuff up on World Class to look at over the break? Not to turn in. I don't want anything else from you. I've got enough. I'm backlogged enough. If you've got stuff for me today, make sure to get it to me. If you don't, who gives a shit?
So
It's
we're done-
fine.
done
I'll
with
get it
homework
from you.
for this
What's that?
Done with homework for the semester then?
Done with homework for the semester. But I do recommend checking some of these out because you might see some of them again on a take-home final. And wouldn't it be nice to have a head start on my take-home final? Just saying. So after my calc class is trying to worm me out of having an in-person final for them too. So
But
it's
calc is manageable as an in-person
it
final.
totally is. But I was thinking we might do it the last week of class. No final.
Surprise.
No finals. week.
No, I wouldn't surprise them with it. That wouldn't be cool. That wouldn't be cool. Yeah, on Monday, I'll just say this with the recording. I said this before. Thanks for working with me on Monday. I just got up and I was just like kind of dead. I just didn't feel like coming in. I was tired. And as I was saying just earlier, because to do this, like my wife always calls it the Dr. T show. She's like, oh, did you do the Dr. T show? I'm like, yeah, I did the Dr. T show. But it wipes me out. Like having to come, just even though I don't know if it seems like it takes effort or not, but it's like exhausting. Even though I love you all and I feel very comfortable here, it's a show where I have to look like I know something.
Well, you're presenting for like an hour and 15 minutes twice a week per class.
True.
That's a lot. And that's a lot.
Oh, you guys are so good for me. Thank you. Yeah, that's right. It's
Yeah.
hard. Yeah. But I didn't want to take off my pajamas. So it was just like, fuck
You
this.
can come to class in pajamas.
But then I have to come to class. I have to leave my house.
That's a bit off.
And your defense, I didn't leave either.
Yes.
I woke up and I saw your email and I was like,
Good. I pictured you being happy and totally cool with it. So I figured everybody would be cool with it. All right, so let's talk about this thing because I want to talk about several aspects of it, and there's something that there's a lot of things going. Honestly, there's a lot going on here. A lot. Did you get anywhere with it, Christian?
Well, so Penelope and I were talking
Oh,
about
cool.
it.
Did you work on it too?
Yeah, a little bit, yes.
We're trying to figure out, so like, kind of following like what we were talking about over here, this would be like the cosets that are like gained from some element of G operate like plus like 3, right? So like, that was another thing. Would you do like, could you rewrite that as like Z mod 3 or like, and then like the external direct sum of like Z mod 3, like could you split it up that way?
It feels like it should work that
But
way,
it doesn't work
but
that
it
way.
doesn't, and that's the
Yeah.
kind of, it's a little wild.
is that because like the direct sum doesn't work in that way? Like you're
Yes.
not just like building so that like the integers plus the integers doesn't really mean necessarily that like they both have to be the same.
Right.
Okay.
Right. So
Yeah,
let's,
I don't really
yeah,
know.
it's okay, it's okay. There is part of it, the mod 3 does show up.
Yeah.
Absolutely, but not in the way you would expect. So let's talk about this. First off, one of the things I noted is that this is just called an external direct sum. So if I have a group and I have another group, two groups, and I form this thing called the external direct sum, I've been using this symbol, like cross product, for that, and it really is the same thing. It's just, I think, notationally you should be aware that it's also called this. There's a thing called an external direct sum and an internal direct sum. External is when you've got two things that aren't related inside some group together and you build a new thing out of them. An internal one is where you've got some subsets of a bigger group, and then from them you form basically this little thing inside the group. And I think here we actually use this symbol here. So this is an internal direct sum where you take a couple subgroups and then look at their cross product, all the ordered pairs of these things. And then this is an external one where these might just be totally weird, unrelated beasties.
Does an external direct sum like imply disjointedness of something, like some form?
Yeah,
Or like where the intersection would be like trivial.
are you saying for an external like this?
Yeah.
Yeah, they don't really have to have any relationship other than their groups.
Okay.
So they could be like weird, like one could be a Z mod something,
Yeah.
another could be a dihedral group. They don't really have to have any commonality.
But if they do have commonality, that's okay too. Like.
Yeah, that wouldn't be, yeah, if they have commonality, it's probably an internal, because they probably share some elements from some bigger structure, so it's probably an internal one. Does that sound okay?
Yeah.
So this is just ordered pairs of these things. G is in G, and H is in H. And the way the group ops work here is you kind of just keep everything separate. It's a lot like vector operations. So this new operation on this thing, I use the operation on G on these first ones. So this is like the G op here, and then here I use the H op on these guys here.
So it's just like component-wise?
Component-wise is the perfect way to say it, yes. Kind of keeps everything separate, but then a new rhythm kind of emerges, yes?
Okay, but then if you're composing G with G prime, how is that not just giving us back an identity?
Say more. So G prime just represents a different, it's not the inverse,
Oh,
which
it's
I
not
think
the
is what,
inverse. Yeah, that's what I'm thinking of.
Yeah, yeah.
Okay.
but it would, you're right. If it was
Okay.
G inverse,
I was
then I
gonna
would.
say, I was like,
Yeah. But what I could get here, there's an identity in this thing, and it's the identity from G, comma, the identity in H. So the identity is a little bit more complex here. If we had more time this semester, we would spend more time talking about these things, like their order and things. But I think that's enough to get this out of here. So let's just look at this guy first. This is notated as Z2, like this, like R2 is the plane, or R3 is three-dimensional space. This is just a grid of integer points in the plane.
So we could write it as a Cayley table?
Oh, a big mofo Cayley table, because it's infinite.
Oh.
So
yeah.
we could.
Like it technically could be, but.
You could, yeah, it's like a crazy, your Cayley, actually, I'm not sure, because this has all the negatives in it, so we could like do some, I don't even know how I'd make a Cayley table out of a doubly infinite thing.
Yeah.
I guess anyway, yeah, it would be beastly. So this is just all the integer points in the plane. It's just nice little grid. It's a lattice of points, which is the mathy word. Does that make sense, what this thing looks like? Which also makes it a little harder to think about. If it was just the plane, it might be easier. So then what we're doing is we're taking this subgroup, this cyclic subgroup generated by the 0.33. Now, what are the operations here? What do you think?
Modular.
Oh, there's no mod yet.
Oh.
Just addition.
Like that's not Z mod N.
Not yet, no.
Okay.
Yeah, so this is just straight up integer. So it's just addition, just normal addition. So if I had like AB plus CD, it's just component wise. It's component wise. Like that. Nothing funky, just pairs of integers and very little geometry. But we are going to still kind of pull in some geometry to think about this a little bit. At least that's how I had to do it. So let's look at this thing. This is all the multiples of 3, 3, where k is just some integer. So it's 0, 0, 6, 6. It's a subgroup unto itself, and it is the diagonal lattice points that fall on multiples of 3. So 0, 0, 3, 3, 6, 6, minus 3, minus 3. It's all these guys. So when you two worked on this, did you were you seeing that? Was that?
Yeah, I guess geometrically, like even if you do like, because we didn't really do, or at least I didn't think of like the direct sum correctly, but if you then add like 3, 3, right? So if you're thinking of that as like the thing that you're modding everything by, right? You could add that to a point like, I don't know, 0, 1, right? And then that like lifts you up.
Yes.
Which is like one of the cosets, I guess.
Absolutely.
And
yeah.
so then with that, that would mean that -1, 0 is also part of that, right? Because if like 0, 1 lifts you up, -1, 0 would like still kind of like lift it up, like it'd be part, like,
Yeah.
I think, yeah.
Yeah, and I think those would actually be two different cosets. Wait, those,
Well, if they're
Those are
like
the same
modded
coset.
by like the,
Yes.
yeah,
yeah.
okay.
Yeah.
So that, yeah.
So this right here says, so this is that cyclic subgroup here. This says all these are the same, and that anything that differs by these is the same. And this is a really hard, weird thing to think about. But what we're doing is we're kind of sewing all these together. These all become one creature. Get this? Yes?
So you're saying anything that counts in that falls into one group, and everything else that isn't that is in a different group?
Yeah, yes. I think. It may be, hold on, that sounds rightish for sure. So I think your brain is doing the right things. So for example, when we take cosets of this thing in that group, when I look at Z plus Z mod this critter here, I'm gonna have cosets that look like this. They're gonna be K times this point. And all of these are gonna be the same. So forever, I've been creating an infinite, this is why making pictures of this or Cayley tables of this would be batshit, because it's just infinite. So these things are what my cosets look like. So now, what is this thing, what is happening here? And what you can do, and here's how I at least wrapped my brain around it, is we are taking, like, so this strip here is the same as this strip here, is the same as this strip here. So I'm saying that like this end here, and think about how this works, the different cosets. So what if we took, let's see, what is this guy here? This would be 6, 0. I'm making these perfect diagonals here, like that. So that's 6, 0. So its companion coset would be 9, add 3, 3 to that, and what do you get? You get 9, 3 out here, and then that's the same as. So every point on this guy has a companion over here that differs by a multiple of 3. The only problem is I don't have all these. If this was the real numbers, if I had R cross R or R plus R, and I was doing this, every coset here on this side would be sewn to this side over here. But all we have are these integer points that we're sewing together. And we don't really move our brain away from those integer points, but thinking of these tubes as being copies of each other is probably the best way to envision this. So in other words, this point is the same as this point is the same as this point, and this is the same as this. So if something differs by 3 plus 3, so for like this guy right here, if I grab that point, and that's just 2 cross, 2 by 2 this way, then its companion down here is going to be this guy. Yeah, kind of, okay. So what we can do is we can say, all right, I've said that this line of integers and this line of integers and this line of integers, they're really all the same. So what we end up having is just one strip. We can think of this whole thing as a single strip. And everything else is just like a hologram of it, or some kind of shadow or projection off into space. But we're folding the plane down and just collapsing it into this one single strip. And this strip is 3 by 3 across. So, I don't know, 3 square root of 2 is its distance, right? If I was Pythagorean theoreming this thing. So what we get is in this direction, we've got mod 3 essentially going on.
So each point in that tube, right?
Yes.
Would that be the representative of a different like coset?
Yes. Yes.
Okay.
So every point in here, and except for like the edge. So like if I took 0, 0, I'm kind of like maybe even
like 0, 0 should be like part of the coset 3, 3.
it is.
Right, and
Yes.
so then like every little element in that tube is just like, it shows up again for like the next tube and the next tube.
Yes.
But like each one individually.
Absolutely.
Okay.
So then is 3, 3 both in that strip and in the next strip?
Yes. Yes.
But 0, 0.
0, 0 is, we just want one representative.
So, but like theoretically, if you were looking at all the representatives, then 0, 0 would also be a part of the -3 strip?
Yes.
Okay.
Yes.
And do we only go in that direction, or can you go the other way too?
Good question. Because there is another direction here, right? There's, right, because these can all, so like in here, if I move in this direction, everything is mod 3, but I can move up this way. I'm gonna have to be able to move up that way and get higher and higher y coordinates, right? And actually slightly different x coordinates as well. But what we're gonna do is we're going to create an isomorphism between that strip and an easier to think about strip. So the strip we're gonna think about, this is how you gain your intuition as to what that thing might look like. And then what we're gonna say is, let's make life easier. Let's, again, look at z cross z. But let's make this edge here, this x-axis, and then let's just move up 1, 2, 3, and make that the top of the strip. And make the, kind of rotate it by like 45 degrees counterclockwise around the origin. Let me stop for a second. Does that sound kind of, it's just so much easier on the brain, right? And what I'm gonna do is I'm gonna set up an isomorphism between what we have here and what we have over here. And from that, we'll actually gain some insight as to what this thing is. So one thing I want you to notice, and Christian, you had mentioned about the mod 3. you can see there's only that mod 3 in one of the directions, and then you've got freedom, complete freedom in these guys here. So, let me grab my notes. I've been going without notes here. I'm not even sure I wrote this shit down here. I wrote it on scrap paper, so I don't know where it is. I guess we'll just see what happens. But I want to create this map phi that's going to go from the group we were given into what I suspect it is, and then show that we have an isomorphism here. So I'm going to take this thing here. Oh man. Yeah, let's just do it. This is A plus. So this is what I'm claiming it actually is the same as. And if you look at the strip, it makes sense, right? The first coordinate can be anything here, and the third coordinate is just a wraparound kind of thing. And I think what we're going to do is we're going to take a coset from here. So we take let's just say AB plus this thing here. And we're going to send that element, so this is a coset. I'm going to send that element to A minus B, comma, B mod 3. Now this was from playing with it for a long freaking time. I don't think that's obvious at all. I will tell you kind of where this came from. Here, this A minus B. This vector, thinking in terms of vectors, this vector 3, 3 is equivalent, if you think about vectors in terms of just direction, to 1, 1. What is orthogonal to 1, 1? 1 minus 1. Right? So what's orthogonal to that is this vector here, which is 1 minus 1. So what I'm kind of doing is projecting things with that A minus B onto this vector here. So if I take AB, or just AB, and I dot product it with minus 1, 1, which is part of the projecting I don't know how much of this you remember from Calc 3, but I was using Calc 3 to think about this. So I was thinking if I projected that onto here, I would get A minus B, and then there's some scaling that I'm ignoring and shit like that. So that's where this A minus B came from. And we can show that this thing is actually an isomorphism. So phi is an isomorphism. I think it's kind of clear that it's onto. Do you take a look at that and see if you believe it's onto? And think first, like if I'm trying to hit something here, so you pick the second component has to be one of these numbers here because everything's mod 3. So pick B so that it hits that, and then once you've set up B to match this guy over here, just set A to be what it needs to be to match this thing out here, right? So A minus whatever that B value is, and you can make this anything you want. Is that making sense? I'm not saying it well. I'm seeing nods, but not a full set of nods.
I'm starting to see what you mean.
What's that?
I'm starting to see what you mean.
You're starting to see what I
just need
mean?
to like think about it.
Yeah, cool. So yeah, so like if I was trying to hit 17.2 over here in that strip, then I would say, okay, well let's let B equal 2, and then set A equal to 19. And then that would get that point.
I see.
So it's an onto map. And A can be anything. A comes from the integers, B can be anything, but I'm gonna mod 3 it, so I'm just picking from 0 to 1. So it's onto, it's 1 to 1, because, shit.
Wait, I'm confused at how your A and B work, because B mod 3, 2 mod 3 would be, if B is equal to 2, 2 mod 3 would be, I guess 2, yeah.
2.
Okay, I see what you mean, yeah.
Is that cool?
Yeah, so you just have to be careful to, like, does it just help to always choose something that's less than 3?
I mean, I don't have to, B could be any actually, Sophie, because this is equivalent, so like I could have said 5 here, but I have to remember that it's actually mod 3.
Okay,
So,
got it.
does that make sense?
Yeah.
Yeah, cool. And then I could have adjusted A accordingly.
Got it.
Yeah.
Yeah.
Nice. So this thing is 1-to-1. If I have phi of A, I kind of don't want to go through the whole damn proof of it.
I trust you.
Is this okay?
Yeah.
This is like, because it would be easier if I could have like started, I gotta like talk about the stuff that was for today to make this easier to talk about. But it's 1-to-1, it's onto, it preserves group operations, which you could prove to yourself pretty easily. So phi is an isomorphism. So this group is the same as this one. So in other words, to understand this, I can just think about that over there. So now I gave you another problem that I'm going to call back on now that you understand how to think about this. The other problem was this, and here's a good fun one to think about. Who knows where you might see it again? I think it was this, or was it? Does it? Yeah. A little different. Little more interesting. Some subtle things will come out of that. So this is a great one to think about. And this is the basic idea. It's something like this, but what? So think about that. Let's see. Speaking of isomorphisms, what time is it? I got like 35 minutes. Speaking of isomorphisms, we could have done this in a slightly different way. And that way is via homomorphisms. So an isomorphism is a 1-to-1 onto map that preserves group structure. I don't always have 1-to-1 or onto. And when I don't, and I just have preservation of group structures, we have a thing called a homomorphism. So if phi is a map from G to H, and these are both groups, because like everything is in here pretty much, right? It preserves group ops, then phi is called a homomorphism. So it's preserving structure. The morph is the structure, and it's saying that they have similar structure but not identical. The iso is identical. This is similar structure. Is a homomorphism of G to H. So let's look at some examples. Probably the best place to start. So for example, example 1, I've got phi that goes from Z to Z4. And phi, we're gonna make phi chill. Phi of X is just, so take some integer X and literally just mod for it. So it takes all of the integers and crushes them down into these 4 different integers, 0, 1, 2, or 3, modulo 4. So this thing here is a group homomorphism. So phi is a homomorphism. And all I need to check that is this, that phi of GH is equal to phi of G, phi of H. So this here is the G op, and then this here is the H op. And you kind of have seen this with the isomorphism stuff a little bit. You just got to keep track of what side you're on. But that the image of each of these things composed gives me the same thing as composing first, then casting the image. So here, if I want to check that, what are my operations here?
Addition and addition mod 4.
Exactly. So here I'm going to take A, B that are integers, and I'm going to do A plus B, and that is equal to, now I go to my formula, A plus B mod 4. This is very trivial because I'm just relying on that modular arithmetic is that mod 4 plus that mod So this is A mod 4 plus B mod 4 as via modular arithmetic, and that's phi of A plus phi of B. So it's a homomorphism. Awesome, that's all I have to check. But I'm interested in how close this is to an isomorphism. So how close is this thing to one and onto? Let's go for some low-hanging fruit. Is this thing onto? Yeah, Cormac, why is that? I agree.
Any integer you put in modular 4 is gonna give you an integer that is modular 4.
Exactly, and then literally I just have to run 0, 1, 2, and 3 through here to get the primary outputs over there. So this phi is onto. It won't always be onto, but it certainly is here. So phi is onto. Let's define something here. Define the kernel of phi. So that's not like Colonel Sanders or anything like that. It's the kernel of corn. The kernel of phi is the set. We write ker phi like that. Is defined to be the set of all G in the input group such that phi of G is the identity in the output group. So it's everything that gets sent to the identity. It's what's getting crushed by this thing. What is being annihilated by this mapping. So let's draw a little picture with this, because there's this one I've got a beautiful picture of. Here I've got Z up here, and I've got 0, 1, 2, 3. Let's just do a little bit in each direction. And then here, I've got my output set, which is just Z mod 4. So I've got 0, 1, 2, and 3. And then phi comes from here and comes down to here. What is going to get sent to 0? Multiples of 4. Anything that's a multiple of 4. So 0 gets sent there. 4 gets sent there. Minus 4 gets sent there. So here we have phi of 4k equals 0. So my kernel is everything that's a multiple of 4. So for this map, our kernel, say kernel of phi, is equal to the set, well, actually we can just write it like that, 4z. It's 4 times the integers, all multiples of 4.
So it's non-injective because like it has a non-zero kernel.
Exactly. So there's infinitely many things getting sent to the identity. This thing can't be one-to-one. And in fact, everything's going to have infinitely many things sent to it. For example, 1 is going to get sent there. What else gets sent to 1?
5.
5, and then
Negative 3 would.
-3, yeah, that was always kind of weird, right? It's a little weird. -3, and then like all that stuff. Notice that what's getting set to 1 is everything up here that is 1 plus 4k, all that stuff gets sent there. Everything that got sent to 1 is of the form 1 plus the kernel of phi. That's a coset, right? Left coset. And that's the solution to everything that got sent to phi. What do you think the solution? So if I have phi of x equals 2, what are the solutions?
2 plus 4k.
Yep, 2 plus anything from the kernel. So like diffie-q people, who's had diffie-q? And almost everybody was kind of, you're in it right now. Okay, but Camilla, you've had it, yeah? Okay, cool. So when you do these linear equations, you've got some linear differential operator on, say, like y, and it spits out some particular thing. Here, think of, so this is a linear operator. So like, 3y double prime plus 2y prime minus y equals, then over here you might have something, who knows what you can have over there. You've got to solve some equation like this. So how do you do it? You first find a particular solution. So you find a y sub p that when you run it through here, it spits out this exact thing. And for this, it's going to be like some multiple of, it's going to be one of these things. You learn to guess.
Don't
Right.
you do it the other way around, like you solve the homogeneous equation first?
Well, we're going to do that. Yeah, it's cool. We'll do that. It doesn't matter which one you do
Okay,
first.
okay.
Yeah, you're right though. And then I solve this one. Or first I solve this one. And I get the homogeneous solutions out of there. Well, the homogeneous solutions are just the kernel of this differential operator, which is linear. So the way this works is you get a yp, and then you find the kernel of the differential operator. This is just your homogeneous solution. And this is all your solutions. And then if you've got some initial conditions, you can narrow this guy down to a particular form of it. But what you're doing is just this stuff. It's really just the things we're just talking about right here. Get that one. So here, my particular solution was the 2. There's other particular solutions. I could have picked like 6. That would have worked too. And then just form that whole coset for the answer. So I just wanted to show you that you've seen this. This is like floating in your life. It's just not talked about this way. What's that?
Would there be like a biconditional then, where like a function or a transformation is injected if and only if the, like, I guess, function applied to the identity of the domain is, or the kernel is like the identity of the domain?
Yes,
Okay.
exactly. And let's put a result up about that. So this kernel gives you a measure of injectivity. The kernel is a measure of how not one-to-one is this thing. And it has an incredible role for it. I think we'll get to that today. But yeah, so here's like some little result. I don't know what we'll call it a theorem. Maybe you'll prove it on some future thing for me. There's only one future thing coming. Theorem that if phi from G to H is a group homomorphism, then phi is one-to-one if and only if the kernel of phi is just the identity in G. And we could prove this. I kind of don't want to right now, just because I want to get to some like meatier stuff, but you could prove this. Proof all you eventually. Yeah, maybe eventually for sure. How about we say that? Someday, next week or two, we'll do that. So this kernel, also some things to notice. Fact, I'll call this one a fact. The kernel of phi is a group unto itself. Let's do a quick proof of that to prove that to ourselves. So proof, I need to check all sorts of things. How about we say subgroup of G? That makes life easier. Then we don't have to do all the stuff. We just have to do the subgroup test and we're good to go. So closure would be this. I'll take A and B in the kernel of phi. Then that means phi of A is the identity in H, and phi of B is the identity in H. And because this thing produces, has group structure preserved, phi of A times B is phi of A times phi of B. And this is the only thing I have. I don't have any other structure to work with. This is the only assumption about phi right here. It preserves group structure. So this is E, this is E, and then this is just E. And that, of course, is that E and H. So AB is an element of the kernel. phi. We can do a similar thing for identities, or for inverses. Let's see, how would we do the inverses? So let's see, inverses. So we'll take, again, we got A incur phi. We need to show that A inverse is in there. Well, let's see. We might have wished we'd proven a big list of things about homomorphisms before we got into this, because there is a big ass list. Yes, you got to prove.
Well, like, couldn't you say that, like, if phi of A is equal to the identity,
Yeah.
you could take, like, you could, the identity is equal to, like, the inverse of the identity, right?
Yes.
And then, would that get you somewhere, like, going, could you just, like, take the inverse of either side?
Yeah,
Or
I
is it kinda-
think
get
that's
that?
the way to go, yeah. So let's left multiply by phi of A inverse, because we do know that this is an element of H, which is a group.
Yeah, yeah.
So, left multiply by phi of A inverse. And yeah, I'm kind of wishing I had my list of things already proven, but then this side just becomes E in the H space. And this over here is phi. Yeah, we didn't get the phi inverse. You can bring that inside, but we're, okay, I got it. How about this? The identity in H is phi of the identity in G. That's a simple property of homomorphisms. Do I need to prove that? Because I can. It should be proven at some point. It can be proven. It's actually pretty chill. Hell, I'm gonna prove it to you. I'm just gonna go with this. So this is equal to phi of A times A inverse for some element A in G. So I can do that inside there. And because this, there we go. Because this preserves group operations, we get this. And so now left multiply by that dude, and you get phi of A inverse equals phi of A inverse, but the inverse is on different parts. I know it sounds the same. We got that. And then over here, now I can bring this guy in. So this is equal to phi of A inverse. And so A inverse is an element of the kernel of phi. Whew. Just gotta like build everything, you know, like you wanna sit down in algebra, you better build a chair, right? Oh shit, now I need to build a cushion. I don't even have a back on this chair, I better build it. All right, so let's take a look at some other examples of homomorphisms. If I make, today, if I make a little video, I'm leaving to go visit my mom on Saturday. Will you watch it before class? You promise. Promise. Okay. All right. Okay. All right. Because we might not get through everything I want to get through today, and we really need to, so that no disappointed mathematicians make my life terrible.
Oh.
There. I can't change their opinion of me. Okay, let's look at another one here. What about phi maps from Z24 to Z24, and phi of x is 4x. Now that is a homomorphism. You could probably look at it and see it preserves group structure. What are our operations on these sets? Addition mod 24. What's the kernel? I would take slow down. Slow down. Certainly that would be in there. I agree. Let's take a look. Look at what we're doing. You're taking things from here and you're multiplying by 4.
Mod 6? Something mod 6.
6.
There's something, so it'll still be mod 24, because we'll still be in that group mod 24, but you're definitely thinking,
Why is it not multiples of 24?
well, I mean, that's part of it, for sure.
There's more, like,
There's a lot more.
Oh, and then all, like, 4x, then that also will be multiples of 24.
Anything that I multiply by 4 and I get 24 or a multiple thereof is in the kernel. So let's talk about this. So the kernel phi is the set of all x in Z24 such that 4 times that x is equal to 0 mod 24. So 6, 0. 4 times 12 is 48. So this kernel is going to be 0, 6. So this is what you were thinking, Sophie. You were saying mod 6, but I knew you were thinking about it
Yeah.
right. Just we don't have the mod 6 though. So 12, 18, and I think then 24, like you guys said, definitely. But it's just that set. Yeah.
That's shockingly simple.
It is shockingly simple. Yeah, you were making it way too hard for sure. Let's look at another example. Or do I want to go to some big payoff result? I've got all these little things that we wanted to do. Oh, let's take the last 15 minutes to do something a little more challenging. Let's determine all the homomorphisms between two groups. And this is a classic problem. And it's definitely a problem I'm going to ask you to do at some point. Oh shit, we probably need a few properties. I'm just going to do these freaking properties and get this shit done. Properties.
These properties of the homomorphism.
Yes, of a homomorphism phi that goes from G to, here I use G bar. Why don't we just shake it up a little? Yeah, that's spicy. That'll wake you up. So some of these I've already proven is that phi of E is equal to E bar, which is the identity in G bar. So it preserves the identity. Did I prove that?
No.
Oh, I didn't. No, let's prove it. So proof. Phi of E is phi of E times E. This is kind of a cool proof. And because I preserve group operations, that's phi of E times phi of E. And now I'm going to right multiply or left multiply by phi of E inverse. So I'm going to cancel one of these out. What do I have on the left? So I'm going to multiply by, so let's say left multiply by phi of E inverse. What's on the left?
E bar.
E bar, right? It's the identity in the output space. And then on the right, I've got phi of E. And that proves it. So that's cool. That's a cool proof. Very elegant. We can also prove that phi of some element G, so let's say G is an element of the group G, phi of G to the n equals phi of G raised to the nth power. You would show that inductively. The fact that phi of G squared, so let's just see really quickly here. Phi of G squared is phi of G times G. Again, just using that same trick. Induct. To do a special case for negatives, work it all out. Also, we have, if this is property 3, I don't know what that weird little attic space is up there. Fill it in with your heart's delight. So if G has finite order, then the order of phi of G divides the order of G. So there's a lot of vertical lines there. These are vertical, Sophie.
Okay.
So this is the order of G, or order of phi of G. and this is the order of G. And this is the divide symbol. So how does this proof go? A little quick proof. We know that, and it's pretty straightforward, that E bar is equal to phi of E. We just proved that. And if the order of G, so let's say order of G is n, so that I have something to anchor onto, then this is equal to phi of G to the n. And because of that property too, this is phi of G to the nth power. So remember this theorem that we had, that if I have a group element and I raise it to some power and I get E, this may not be the order, but the order divides this. Let's see, so like, yeah, the order of the group divides this exponent here. So since I have something raised to the nth power giving me the identity, that means that the order of that thing divides the order of, looking at my proof, what the fuck are you talking about, bro? So the order of this thing, that, and maybe we should have known that the order, no, because that's just, so the order of phi of G must divide n. There we go, that makes sense. Do you see why that's true? This, I just lost my bearings for a minute. So for example, like over here in Z24, if I take 4 and I raise that to the 6th power, that's 6, I will get the identity 0 out of that, and this is like 6 times 4 here. I don't know if this is, sorry. Is this making any sense? I'm just like not sure. I'm trying to read, I'm feeling like I'm spazzing, like I've got that I'm spazzing kind of feeling. No? Doesn't seem like I'm spazzing? That's weird, isn't it? You know what I'm talking about though? You start to get that feeling like when you're presenting for 15 minutes on bullshit and you're just like, this isn't bullshit, this is way better than what you guys had to present. But at some point you're just like, am I like saying words I don't know anymore? And this is the order of G. So that is the order of G. So I've proved the thing. So the order of the output for an element divides the order of the input is a good way to think of that. And that is something we will use pretty often. Also, the kernel of phi is a subgroup of the input space G. We already proved that, I think, didn't we? Yeah, we did prove that. But more, it's normal. And in fact, kernel of phi is normal in G. And that's good because we're gonna take that and mod it out a lot. So let me tell you, just like give you a preview, why this matters. We're gonna take some homomorphism from G to H, and it might not be 1-to-1. So what we're gonna do is we're gonna find its kernel, and we're going to mod out all the not 1-to-1-ness from the function itself, from the mapping itself. So we're gonna create this induced map phi that goes from G mod the kernel to H, and it's gonna totally agree with this function everywhere it needs to, but this will become a 1-to-1 map. We're modding out the non-1-to-1-ness. And I think we're gonna have to do some work with that before that makes sense to you at all. I think I might not prove that guy either and leave that as a proof to the reader.
Did that kind of go along with like the thing that you were talking about in the video where the factor groups are isomorphic to the group of inter homomorphisms?
That's part of this, yeah, where we mod out the center,
Yeah,
yeah,
okay.
absolutely. So I don't even think I proved it, but that is a
I think
really.
you like did a little.
Oh, I kind of talked about
Yeah,
it,
yeah.
right? We're like modding out the commutivity.
Yeah.
Yeah. Did that make sense?
Not really.
Okay.
It made sense like when you were talking about how if your element in your inner automorphism is like part of the center, then obviously it's just gonna be like the identity.
Right.
Like your map would become the identity.
Commute everything.
I was
yeah.
getting lost when you don't have an element of the center as like your element that you're using for your inner automorphism. Is that just like it wouldn't be the identity then?
Right, exactly, because once you take out all the things that do commute, all you're left with are these cosets of things.
Oh, and then you get everything.
And this holds the commutivity, and
Uh-huh.
then this representative is not commutative. Because if it was, it would absorb into here,
Yeah.
and it would be part of the center.
Okay.
So what you do is you create a bunch of not commutative things, and so that when you form that map,
It's kind of like the particular solution for like the.
yeah.
Yeah.
Yes,
Okay.
yes, very much like that. Maybe I owe you a proof of that. That sounds like something I owe you. I'm sure I'll totally remember to do it. So let's look at another one that kind of plays off this, is that phi of A is equal to phi of B. And this is getting to what I was just saying here, but it's making it a little clearer. So the output of a homomorphism for two different inputs is the same when these two are the same coset of the kernel. So this is if and only if that holds true.
And that's A operated on the kernel?
That is the coset. So this is
Oh.
A. This is the left coset of A for the kernel.
Okay.
Does that make sense?
Yep. Yeah.
So again, here we're modding out any potential not one-to-oneness that may have occurred here. Here, there's a little proof of this thing. Let's do a tiny proof. At least I have a proof sketched out here. God knows what we'll find when we go into it. So I'm going to do this direction. In other words, I'm going to assume that phi of A is equal to phi of B. So assume phi of A equals phi of B. And then I'm going to left multiply by phi of A inverse, and I'm going to get E bar with my output identity equals phi of A inverse phi of B. And then I can bring that inverse inside by something mentioned previously. So that's phi of A inverse phi of B. And then because this preserves group structure, we can go back and pull it all into one. So we haven't really gone in that direction yet. And what I've got now is that A inverse B is an element of the kernel of phi because the output is equal to this. We have this result for cosets that we talked about what seems like a gajillion years ago, is that two cosets are identical if and only if A inverse B is an element of the thing where the subgroup we're taking the cosets out of. So here, I've got this, I pull it here, so this tells me that A kernel phi is B kernel phi. So lots of structures being built upon structures. And then I got one last one. I'm gonna pop this one up. Bless you. Appreciate it. So I will make you a little video. I don't know when it's gonna happen. Like I'm leaving sick. You're like, yeah, we won't be on it the first weekend, right? Like you're not like jonesing for it for this coming weekend. But I'm leaving to go help my mom on Saturday morning, and I've just got so much shit. I'll be back on Thanksgiving Day, so it'll probably be next weekend after. So last property here is that we're gonna suppose phi of g equals g prime. Then phi inverse of g prime. In other words, all of the things, bless you, all the things that hit g prime is equal to g times the kernel of phi. Let me do a quick example. Let's do a quick, very quick example. I think I've got one here with the u's. I kind of hope I do. No, bless you. Bless you. Well. Oh, okay. Here, I'm just gonna make up some shit. I think we can do this example, and then we'll be done. Suppose that phi maps from U30 to U30, and phi of 7, and that's definitely in there, equals 13. If the kernel of phi is equal to the subgroup 1, 11, and you can check this out, this actually is a subgroup because 11 squared is 121, mod 30 is 1, so this is a nice little subgroup. Then all solutions to phi of x equal 13 are just my particular, so this is a particular solution that spits out 13. I'm gonna take that particular solution and then operate with kernel phi using that result that I just had up there. So this is all the solutions. So x is an element of 7 kernel phi. In other words, x is an element of 7 times 1, 11. And that's equal to 7, and then 77 mod 30 is 17. So these are both the solutions then. And it's just like I'm adding on a homogeneous solution, diffie-q people. I'm taking a particular solution plus the homogeneous version and getting a new one. Okay, that's probably enough. I have to go to some, I need like a little thing for you guys, so I can always just turn off the video.